Hello everyone, welcome to this lecture on the Gram-Schmidt process. Today we will explore what the Gram-Schmidt process and how it works. The Gram-Schmidt process is a method for orthogonalizing a set of vectors in an inner product space. In simple way, just it is used to convert linearly independent vectors into a set of orthonormal vectors. So what is orthogonalization? It means the vectors what we have perpendicular to each other. Orthonormalization means making them into both orthogonal and also of unit length. Let us see how the process goes. So firstly, let us start with the vectors. We have the basis x1, x2, so on, xn. So n linearly independent vectors. So we have to find orthogonal vectors. So that is v1, v2 and so on vn. Then we have to normalize this b. So that is u1, u2 and so on un. So we have to start with the vectors x1, x2, xn, and our aim is to obtain the orthonormal vectors. This is orthogonal vectors and this is orthonormal vectors. So orthonormal means it is both orthogonal and of unit length. So let us see the procedure now. Firstly, we keep the v1 is as it is x1, first vector. So we are firstly obtaining orthogonal vectors. For that, we keep first vector x1 as v1 as it is. Next, the second vector v2 is subtraction of projection of x2 on v1 from x2. So this can also be written as x2 minus inner product of x2 and v1 divided by inner product of v1, v1, v1. Next, we obtain the third vector v3 is similar way x3 minus projection of x3 on v1 again minus projection of x3 on v2. So you can also write this as x3 minus inner product x3 v1 divided by inner product v1 v1 and the v1 vector minus x3 v2 divided by inner product v2 v2 into vector v2. In this way, we continue for n orthogonal vectors. This is xn minus projection of xn onto v1, projection of xn onto v2. Like this it goes minus projection of xn onto vn minus 1. So now we get the b dash orthogonal vectors v1, v2, v3 and so on vn. Now we have to orthonormalize it. So that is, and also we have to check that vi, vj for orthogonalization should be equal to 0 for all I not equal to j. Then let us make orthonormalization, that is u1 is equal to first vector v1 divided by norm of v1 and u2 is equal to v2 divided by norm of v2 and u3 is equal to v3 divided by norm of v3. Like this it will continue. These vectors are form orthonormal set. Orthonormal set. This is our expected result by Gram-Schmidt process. Let us take an example here where if W is equal to span of the vectors x1, x2, x3, where x1 is the vector 1, 1, 1, 1 transpose, x2 means column matrix, 0, 1, 1, 1 column matrix, x3 is 0, 0, 1, 1 column matrix. Construct orthonormal basis for W using Gram-Schmidt process. So we already seen the procedure how to construct, how to obtain the orthonormal basis for the given basis of the vectors. So let's start step by step now. So firstly we have to find the orthogonal vectors. First step is we have to obtain the orthogonal vectors. We have to find orthogonal vectors v1, v2, v3. Secondly, we have to obtain the orthonormal vectors. That is our final expectation. Orthonormal vectors u1, u2, u3. So let's start step by step. Firstly, we keep the vectors. First vector as it is. Means we are going to find v1, where v1 is x1 itself. That is the matrix, column matrix, what they given as it is. Next we find v2 by the formula. It is x2 minus projection of x2, that is inner product of x2 v1, projection of x2 onto v1. So you can write inner product of v1 as norm of v1 square into v1. So we find the inner product of x2 into v1. This is x2 transpose into matrix v1, where x2 transpose means 0, 1, 1, 1, and matrix v1 is 1, 1, column matrix v1. Taking this product, we get it is 0 plus 1 plus 1 plus 1, it is 3. Next we find norm of v1 square, that is square root of what element present here, 1 square plus 1 square plus 1 square. So we get not square root because we have the square here. So it is not under the square root. 1 plus 1 square plus 1 square plus what we have here, plus 1 square plus 1 square, it will become 4. Therefore, v2 is, where x2 is what? x2 is column matrix 0, 1, 1, 1 minus, and this we got 3 and this we got 4. Therefore, it is a 3 by 4. And the v1 vector is 1, 1, 1, 1. So we do simplification of this. Gives us the result 0 minus 3 by 4, minus 3 by 4, 1 minus 3 by 4, 1 by 4, 1 by 4, and 1 by 4. So this is the second orthogonal vector. Now let's see the third one, where v3 is according to the formula, it is x3 minus projection of x3 onto v1, that is x3 inner product of norm v1 square v1 minus projection of x3 onto v2, we write like this, to v2. Now we substitute and simplify, where x3 is what? So our x3 is, first let us find the inner products of what we required. So x3 v1 inner product. So our x3 matrix is, we have to take it is x3 transpose into v1. Therefore row matrix only we have to take, it is 0, 0, 1, 1, and where v1 is 1, 1, 1, 1. So doing simplification gives that 2. And let's find x3 and v2 inner product, that is x3 transpose into v2 where x3 transpose is 0 0 1 1, where v2 is we got minus 3 by 4 1 by 4 1 by 4 1 by 4. So matrix multiplication row with the column, we get 1 by 4 plus 1 by 4, it's a 2 by 4, can be written as 1 by 2. So 0 into this, 0 into this, 1 into this, plus 1 into this gives 2 by 4, where 2 by 4 can be written as 1 by 2. Next we find norm of v1 square already over. So next we will go with v2 normalization of v2 square, that is we have v2 is what minus 3 by 4, squaring that 9 by 16, 1 by 4, 1 by 16 3 times. So we have here the elements of v2, squaring of these and taking summation, we get 9 plus 3 12 by 16. So 12 by 16 can be simplified as 3 by 4. Now we find what is v3 orthogonal vector. So it is according to the formula x3, where x3 is 0 0 1 1 minus the inner product of x3 2 by what is v1 2 by 4. So 2 by 4 of v1, it is 1 1 1 1. Next we have x3 into v2, so that and divide by 3 by 4, it is minus 1 by 2 divided by 3 by 4 of v2, it is minus 3 by 4, 1 by 4, 1 by 4, 1 by 4. So you can simplify this as, I'll keep the first vector 0 0 1 1 as it is, and since it is 2 by 4 can be written as 1 by 2, I can write the vector is 1 by 2 1 by 2 1 by 2 1 by 2, and you can take this write 2 by 3. So minus 2 by 3, taking inside we get minus 1 by 2. What do we get? Minus 2 by 3 multiplying inside, I'll get minus 1 by 2, and 1 by 4 into 2 by 3, I'll get 1 by 6, 1 by 6, 1 by 6. So simplification, final simplification gives us finally 0 minus 1 by 2 plus 1 by 2 0, then minus 2 by 3, 1 by 3, 1 by 3. So take simplification, 0 minus 1 by 2, minus into minus plus 1 by 2 0, 0 minus 1 by 2 minus 1 by 6 gives us minus 2 by 3, 1 minus 1 by 2 minus 1 by 6 gives 1 by 3, again the last also say 1 by 3. So we have the basis, so orthogonal basis, B is given x1, x2, x3. Now we got B dash. It is v1, v2, v3 orthogonal vectors. Also we have to check inner product of the vectors satisfying the condition 0. So let's check v1, v2 inner product. It is where v1 is what? v1 transpose into v2. So where v1 transpose can be written as 1 1 1 1, and v2 we got as minus 3 by 4 1 by 4 1 by 4 1 by 4. So this product is 0 because you have that minus 3 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4 gives 0. Next we check that v1 V3 inner product means V1 transpose into V3. So that is 1, 1, 1, 1, where V3 is 0 minus 2 by 3, 1 by 3, 1 by 3. This also satisfies the condition 0. Next, we also check that V2 and V3 are orthogonal or not. So where V2 transpose into V3, where our V2 matrix is minus 3 by 4, 1 by 4, 1 by 4, 1 by 4, and V3 matrix is 0, minus 2 by 3, 1 by 3, 1 by 3. So taking the product of these gives us 0. See, it's 0 minus 2 by 12 plus 1 by 12 plus 1 by 12 satisfies the condition. So we got that V1, V2, V3 are orthogonal vectors. Now we have to make them to orthonormal. So how to normalize it? So it is very simple. First let's find norm of every vector. Norm of every vector, where V1 is 1, 1, 1 vector. So square root of it is not a square, so therefore we have to consider it's a square root. So we have the square elements are 1, 1, 1, squaring it. 1 square plus 1 square plus 1 square plus 1 square. So this gives us square root of 4. Next, V2, normalization of V2, square root of, we have the V2 elements are minus 3 by 4, that is 9 by 16, 1 by 4, 1 by 16, so it repeats 1 by 16, 1 by 16. So it is square root of 12 by 16 can be written as, we have 12 can be written as root of 4 into 3 and 4, therefore is 2 root 3 by 4, or you can write root 3 by 2. Next we can take norm of V3, so that is square root of where V3 is 0 square plus 4 by 9 plus 1 by 9 plus 1 by 9 can be written as 6 by 3, root 6 by 3. So where root 6 can be written as root 2 into root 3. So therefore you can write it is 2 by 3 under the root. Now therefore what is U1 is V1 by norm of V1. So where V1 is what? 1, 1, 1, 1 divided by norm of V1 can be written as 1 by root 4, 1 by root 4, 1 by root 4, 1 by root 4. So we have the vector V1, divide that by root 4. Next, U2 is V2 divided by norm of V2. So we have the vector V2 there, you divide by root 3 by 2. So we divide by root 3 by 2. So we have here minus 3 by 4 divide by root 3 by 2 is root 3 and 2. So we get here minus root 3 by 2, first one. Next we have that the second term is 1 by 4. So 1 by 4 divided by root 3 by 2. So can be written as 1 by 2 root 3. 1 by 2 root 3 and it repeats 1 by 2 root 3, 1 by 2 root 3. Similarly, we find the third vector U3 is V3 divided by norm of V3, where norm of V3 is what? Root 2 by 3. And V3 we have that 0. 0 divided by anything is 0. And the second we have minus 2 by 3 divided by root 2 by 3. So it gives minus root 2 by 3. And the third we have 1 by 3. So 1 by 3 divided by root 2 by 3. So can be written as root 6. So 1 by root 6 and 1 by root 6. We also check these vectors are orthogonal or not. Means u1 cross product miss. So let's check these are 0 and u1, u2, u3 0. So then u1, u2, u3 is orthogonal. Also we have to check that norm of u1 should be 1 equal to norm of u2 and norm of u3. Let's take one checking here. Norm of u3 is square root of, here we have 0 plus 2 by 3 plus 1 by 6 plus 1 by 6. If you take the LCM is 6 under the root, so we get that here 6 plus 1 plus, so sorry, it is 4. 4 plus 1 plus 1. 4 plus 1 plus 1. So get cancel. So we get root 1 is 1. So like that we should get this condition also satisfied. Then you can say u1, u2, u3 are orthonormal vectors. Orthonormal vectors. This is what we required from the Gram-Schmidt process.